Okay, differentiation lesson number 8 is stationary points. Now in the last lesson we looked at how to find out a point on a curve, whether it was increasing, so going up the way, or decreasing, going down the way. We looked at our gradient. If it was bigger than 0 it was increasing, if it was less than 0 it was decreasing. What we're going to focus on this time is the points where it's neither increasing or decreasing. It's stationary. There's like a small hesitation in the function. So this function is increasing and increasing, and at the top, at this turning point, it's stationary momentarily, and then it's decreasing. Then it's stationary, increasing, stationary, decreasing. So these stationary points are important features of a function, and we want to be able to find out where they are without having to plot the whole graph. So we're going to be finding out where these points are by looking at their gradient. Now in increasing curves we get a positive gradient, decreasing curves we get a negative gradient. At a stationary point the gradient of the tangent would be 0. It's a horizontal line. So what we're going to be doing is we're going to be differentiating the function so that we get an expression for the gradient. We're going to be saying where are the values that this is equal to 0, because I know that's where the stationary points will be. So we'll make our derivative equal to 0 and we'll solve it. Now sometimes, like this curve, has 3 stationary points, so sometimes there'll be 3 answers. Sometimes there'll be 2, sometimes there'll be 1. There could be any number. When we're finding the stationary points, we won't just want to know where the stationary point occurs, we want to know what type it is. So here, this stationary point here is a maximum turning point. So we're getting to our highest point and then we're coming down again. Here we've got a minimum turning point, so it's at the bottom of the curve and we're coming up again. Another maximum and then down. These ones we're familiar with. There's a couple of extra ones that we're going to be looking at also. And these are called of inflection. So in this function, we're increasing and increasing. We're stationary temporarily, and then we're increasing again. And that's called a rising point of inflection. Similarly, we can get a decreasing curve that hesitates and then decreases again. That's a falling point of inflection. In your notes on page 13, there are some pictures of the various types of stationary points. Please look at those and familiarise yourself with the shapes. Now I've just sketched here a couple of parabolas underneath to illustrate the maximum turning point and the minimum turning point. Now on a maximum turning point, just before the turning point, the curve is increasing, and just after the turning point the curve is decreasing. For a minimum turning point, just before that point it's decreasing, and just after that point it's increasing. So once I've found the actual turning point, the x value itself, what I'm going to then do is have a little look just before that and a little look just after. And by looking at either side of it, I'll be able to work out, is it a maximum turning point? Is it a minimum turning point? Rising point of inflection? Or a falling point of inflection? We'll do that using a nature table. Okay, we're going to enter our notes on page 15. We're asked here to find the stationary points on this curve, y equals x cubed minus 6x squared plus 9x minus 4, and to determine the nature of any stationary points that we find. So the first thing we're going to do is we're going to differentiate. It's straightforward, it's ready, I don't need to do any preparation here. So dy by dx is equal to 3x squared minus 12x plus 9. Now we need to remember that for stationary points our gradient is equal to 0. So we're going to take this derivative, 3x squared minus 12x plus 9, and we're going to make it equal to 0. And that means we'll find the values here where we have stationary points. I'm going to factorise to solve this. When I look at, first of all, there's a common factor of 3, so I'm going to divide everything by 3. X squared, oops, that's x squared, minus 4x plus 3 is equal to 0. And then I'm going to factorise. That's x minus 3 times x minus 1 equals 0. And I'm going to solve. So x is equal to 3, or x is equal to 1. This means there are 2 stationary points on this curve. So far we've calculated the x coordinates of both points. So what I'm going to do next is I'm going to calculate the y coordinates. So then I'll have the actual 2 sets of coordinates. And then for each one, we'll work out the nature of those points. So are they maximum turning points, minimum turning points, rising or falling points of inflection? I'm going to calculate the y coordinates by substituting back into the original function. Be careful that you don't accidentally use the derivative instead. Remember, we're finding points on the original curve. So when x is equal to 3, y will be equal to 3 cubed minus 6 times 3 squared plus 9 times 3, take away 4, which is 27. Take away 6 times 9 is 54, plus 27, take away 4. 27 plus 27 is 54, take away 54 is nothing, minus 4 is negative 4. So my first set of coordinates, 3, negative 4. Okay, now I'm going to do when x is equal to 1, same way. Y is equal to 1 cubed minus 6 times 1 squared plus 9 times 1, take away 4, which is 1 minus 6 plus 9, take away 4, which gives us 0. So our second coordinates 1, 0. So now, so far, I know about this curve that I have a turning point, well, I have a stationary point at 3 minus 4, and I have a stationary point at 1, 0. What I don't know is what those stationary points look like. Are they maximum turning points, minimum turning points, or points of inflection? So that's what we're going to work out next, the nature of the stationary points. Now all the information that we're going to be gathering here, we're going to keep in a table. We're going to be looking at a value of x, we're going to be looking at the corresponding value for the derivative, dy by dx, and then we're going to look at something called slope. Now I'm going to first look at the point 3, negative 4. So the x coordinate was 3. And what I want to do is I want to look at a point a little bit before 3, another point a little bit after 3, and see what's happening. Now I know that at point 3 my derivative is 0, because that's what I calculated. I made my derivative equal to 0 and saw which values that was true for, and 3 was one of them. So I know that when I've got an x value of 3, my derivative is 0. A little bit less than, I'm actually just going to use the number 2, and a little bit more than, I'm going to use the number 4. And I'm going to work out what the derivative will be 2 and what the derivative will be at 4, because I'm actually interested in the gradient at this point. So remember, when I'm doing substituting now, I'm not substituting into the original function, I'm using the derivative, which was 3x squared minus 12x plus 9. I'm going to put a 2 in, so 3 times 2 squared minus 12 times 2 plus 9. 3 times 4 is 12 minus 24 plus 9. Now at this point I can tell it's going to be negative because the 24 is bigger than the 12 and the 9, but I'll calculate it fully, so it's negative 3. But in my table, all I really need to know is that I've got a negative value there, because that tells me that I've got a negative gradient, and it means I know what the slope is going to look like. So now I'm going to do the same calculation for 4. So 3 times 4 squared minus 12 times 4 plus 9 is 3 times 16, which is 48, minus 12 times 4, which is 48, plus 9 gives me an answer of positive 9. So this time the slope is positive. So you see in my chart now I know that my stationary point is at 3, and a little bit before that I've got a decreasing curve, and a little bit afterwards I've got an increasing curve. So if I was to think about what the shape of this curve was going to be, I'd have a negative gradient, got a stationary point, and then I've got a positive gradient. And what we've calculated here then is that our stationary point 3 is a minimum turning point. So we can say we have a minimum turning point at 3, negative 4. Now we're going to go through the same process for the second stationary point that we found, which had an x-coordinate of 1 and a y-coordinate of 0. So we start by creating the table. So x and then dy by dx, and then the slope. This stationary point occurred when x was 1, so I want a little bit less than 1 and a little bit more than 1. So a little bit less than 1, I'm going to be looking at 0, and a little bit more than 1, I'm going to be looking at 2. Now I can fill in the derivative when x is equal to 1, because that's 0, that's my stationary point, and I'm going to be using the derivative to calculate the values for 0 and 2. So I'm using dy by dx, which was equal to 3x squared minus 12x plus 9. So first of all I'm going to substitute a 0 in. When x equals 0, we've got 3 times 0 squared minus 12 times 0 plus 9, which gives us 0, take away 0, plus 9, which is positive 9. So in my nature table here, I can put a plus. Now when x is equal to 2, we actually already used 2 in the previous one, so I really don't need to calculate it again. I'm going to do it here just for completeness, but you don't have to do that. So I've got 3 times 2 squared minus 12 times 2 plus 9. which was 12 minus 24 plus 9, which was negative 3. So I have a negative derivative at 2. So now we can see that at this stationary point, a little bit before it, I've got an increasing curve with a positive gradient. I'm stationary, and then I've got a decreasing curve with a negative gradient. So the slope is going to look like this. Positive is up, stationary, and then negative is decreasing. So now I've got a maximum turning point, which on the graph is going to look a little bit more like this. But these lines are just to give us an idea of the shape so that you understand the nature. So I can conclude that I have a maximum turning point at 1, 0. And I've now completed the question. This function has two stationary points, a minimum turning point at 3 minus 4, and a maximum turning point at 1, 0. So to summarise what we did, because there's quite a lot of steps there, the first thing we did was we differentiated the function. The next thing we did was, once we got the derivative, we made it equal to 0, because we wanted to find the points that have a gradient of 0. Then we solved this equation to give us the values of x. Remember, when we factorised in this case, we had to take a common factor out first, then we were able to use a trinomial. Always check for a common factor first. You can also be using a difference of two squares. You might not be able to factorise if the numbers are not whole, in which case you'd use the quadratic equation or completing the square. Once I have the x coordinates, I need to calculate the corresponding y coordinates. We calculated the y coordinates by substituting the x values into the original equation. Once we have the stationary points, we create a nature table for each one. Within the nature table, we looked at the slope both before and after the stationary points so that we could determine the nature. When we were looking at the slope before and after the stationary points, we were substituting those values into the derivative because we were calculating gradient rather than an actual point. By looking at the nature before and after the slope, we were able to conclude what the nature of our stationary points actually were. There's a summary of steps in page 14 of your notes. You might want to annotate those slightly with your own wording so that you remember the order in which you're doing things. So there's quite a lot in the lesson today, so let's just check that we understand the basic things. What is a stationary point? What does it look like on the function, on the graph? After differentiating the function, what's the next thing that you've got to do? It's very important that you've got this explicitly written on your page. And number 3, what are the 3 rows that you've got to have in the nature table? And number 4, what are the 4 possible types of stationary point that you can conclude at the end? We're not ready to move on quite yet. There's a second lesson on this, 1.8b, and then we'll be ready to go on and do some exercises.